Welcome everyone. So this is the second session for the day, and this session will be on physical and clonable functions. There will be 4 talks which will be presented during this session. So let's get started with the first talk. The title of the paper is When the Decoder Has to Look Twice, Clock Glitching Above Error Correction. So the authors of this paper are Jonas Rushdie, Mikkel Gruber, and Mikkel Pate. And the talk will be given by Jonas.
Thank you for the nice introduction. So what I want to present today is a clock glitch fault attack on the error correction part of a path key storage system. So path key storage system, that for us means something like the fuzzy commitment scheme, where we have a one-time enrollment phase where which we use to store a secret key. And whenever we need that key again, we carry out a reconstruction phase where we do another path measurement and use that together with public helper data to rederive the key. Because the path measurement is non-ideal and a bit noisy, we need some error correction in that system, and we are going to attack that error correction at its very input to extract the code word and therefore also the secret key. As a context, why are we doing this? There are physical attacks on the path primitives already, so side channel and fault attacks, and there are attacks on the helper data schemes where helper data manipulation itself can sometimes be enough to compromise the system. There's also by Merle et al. A side channel attack on the error correction code of such a system, but this work is actually the first fault attack on that part. I'm going to go over the attack itself, how it works on a bit level, and how we actually verify that it works in practice, what our experiment looked like. Then I'm going to say a few words about masking, which might be in place as a side channel countermeasure on the system, how the attack is influenced by path noise, and last but not least, a more realistic, much more limited attacker model, and if the attack is still possible there. Our attack scenario is that, of course, we have physical access to the device. We are going to insert clock glitches, which is not going to be possible otherwise. We want to repeatedly trigger such a reconstruction phase where we rederive the key from the path measurement, and then we need a pass-fail result if that derived the same key or not. Then we need a rather special assumption here. We need a serial data transfer of the codeword to the decoder. That might seem a bit odd, but in the path context, you are quite often limited in space, and a space-optimized decoder is quite often a serial implementation. So we have that assumption naturally. Initially, we are assuming a very powerful attacker. That attacker can operate the device at its optimal operation point, so have an essentially noise-free path response. That attacker can read and write the helper data. Also, usual assumption, because in a path key store scenario, you don't have secure non-volatile memory, so the helper data is often considered public. And then we also do profiling and attack on the same device. Later, we will see that the attack still works in a much more limited scenario as well. For the attack itself, we are looking at the serial data transfer of the code word, as seen from the decoder. So we have the clock line and the data line here, and we see at the rising edges the clock bits are sampled. When we now introduce a clock glitch, we see that we sample one clock bit twice and skip the next one. That means we effectively, in our code word, replace one bit by its preceding value. In other words, we change the code word by a single bit if and only if those two code word bits are different. So that's one single bit change. It's still an error correcting code. It's not going to do much. So we use helper data modification to insert additional bit flips, bring the decoder right to its error correction limit, and then that single bit flip will make a difference. And if we now observe that the reconstruction fails, then we know, okay, these two bits have been different originally. If it succeed, then we haven't made a change with our glitch, and the bits G and G+1 are the same. So we repeat that process, for all 2 bits in the code word and recover n-1 code word bit differences in an n-bit code word. So we basically have the whole code word except for 1 additional bit we have to guess. To test if that works in practice, we constructed a simplified system where the path itself and the usage of the key is completely out of scope. That's why you see these as inputs and outputs here. For the code itself, we used a repetition BCH decoder concatenation, which is quite a usual choice in the path domain. In the following, I will be focusing on the BCH decoder because that naturally is implemented in a serial manner. So when we are talking about the code word bits, we are talking about these 127 bits. The repetition decoder is still in there because, as we'll see later, its delay performance is important for the attack. Around that system under attack, we wrap a design which provides a glitchy clock to that design. So we have an on-chip glitch generator on our Arctic 7 FPGA test system. The procedure for the experiment will look like the following. First, we have a profiling phase where we use 1 random key per FPGA board and estimate the observable data dependency for the several glitch parameters and optimize that to find the optimum individually per board. After that, we carry out the attack as I outlined before. So like the extract all bit differences on 15 FPGA boards with 100 random keys per board, so 1,500 keys in total. And we also don't do this just once. We extract the key from the average of multiple trials. I put a maximum of 250 here to estimate how much can we extract in total. We'll see later that much less will be enough. It makes sense to first look at the glitch effect we actually see, and this plot shows basically how many reconstructions fail if we glitch at a position in the code word and insert some additional helper data bit flips. What we expect to see is that we need to insert 10 bit flips because that is the error correction limit of the decoder, and anything less will not give a fault observable result, and anything more will always do it. What we actually see is something like this, which looks quite different. And we have a number of black bars where the reconstruction always fails with a glitch. So we cannot extract data here. And we have a behavior where we already see the full data dependency at 1, 2, or 3 helper data bit flips. So we can already extract data there, which we will make use of later. But important to note here is it also works as intended at 10 bit flips. So while the model is a bit inaccurate, it still is absolutely working for our purposes. The attack itself, if we carry it out, leaves us with 14.8 bit extraction errors in the code word. If we define those by naive guessing, try to find those via naive guessing, we need to guess around 25 bits after the attack from our down basically from our 64-bit key. We can go a bit smarter than that. So we guess these bits first that seem to be a bit unreliable, that provided different results over our trials. So we do a maximum variance strategy here. And then we need on average only 10.4 bits to guess. And if you look at the attack progress here, you also see that the 250 trials are nowhere near necessary, and already at 10, you're basically done here. If you have a posterior information, so where are the likely extraction errors going to be, we can use that to also improve our guessing strategy, and we are down to 8.6 bits we need to guess. Masking has been proposed by Merle et al. In their side channel paper as a countermeasure, where we randomize the input of the decoder via an additional mask. So from our original data path, we insert a randomly generated BCH code word and subtract it after the decoding. It might actually also help against our attack because we are extracting that input of the BCH decoder, and if we only get one share of that, then it's not going to help us much. For our purposes, we tried 2 different implementations. First is we only mask the input of the BCH decoder And second, we also include the repetition decoder here. That is a slight difference because we need to mask all inputs of the repetition decoder. So A is slightly less overhead. I'm going to start with A, where we only do that at the repetition BCH decoder input, and we see that the attack actually works even better in this case. So why is that happening? Why are we going? Why do we extract all codebit bits perfectly, despite there being a mask? Well, the mask is basically there at the BCH decoder input immediately, while the code word has to propagate through the repetition decoder. So the code word is later there, and we can place a glitch in that gap between those two, and effectively construct a clock waveform where the mask is sampled normally, but the code word bit has the same effect as before. And anything we change with the glitch is only based on the code word and not on the mask. So the masking is completely useless here. So this is maybe a bit similar to glitching in the side channel domain. Here we actually actively add a clock glitch in that delay mismatch. So based on that reasoning, we would expect the other technique to work way better, because there we expected the delay to be well matched between mask and code word. And indeed, if we look at the attack progress, you see that it does impede the attack quite a bit. On the other hand, there is still data to be extracted. On our best attackable board, we are left with 19 bits to guess on average after the attack. When in a scenario where the attacker might choose the best attackable board, you might still consider this to be broken. Also, we see that the data dependency goes in different directions here, and that's exactly what happens when the timing difference goes in one and the other direction. So we see, okay, the masking and code word delay matching is basically too close to be any practical for a design. So far, we haven't considered puff noise, so the puff response was completely constant throughout the experiment, but it still has, on a real-world system, probably an impact on the attack. For this, we split the puff noise into two parts. So first, we have a constant offset. This is possibly due to aging, and we assume this to be constant throughout the experiment. This offset can be extracted and then later compensated through helper data manipulation, so we'll leave it out of the question right now. What remains is actual measurement noise, which is different from measurement to measurement, which we then in our experiments model as IID measurement noise and test it for different bit error rates. What turns out is that the repetition decoder here helps us quite a lot. So for bit error rates below 11%, we have on average half a bit wrong or less than half a bit. So the attack progress is maybe a bit slower, but through averaging multiple trials, we can basically recover our data. And for realistic puff error rates, it's basically unimpeded. Last but not least, I said I was going to introduce a more realistic attacker notion. So we are no longer allowing on-device profiling. So we profile one device and attack another. Also, we now consider helper data manipulation detection schemes. So we allow neither helper data reading nor writing. And what we allow the attacker to do is to increase the puff noise. So you can imagine you might heat up your device to insert additional bit flips in the decoding process through puff noise instead of helper data manipulation. What turns out is the attack is significantly slower. It's about a factor of 10, but more importantly, it still works. We have the cross-device profiling, which worked well on the majority. On 3 boards, it didn't really work all that well. So on these, it didn't perform that good. But on the best attackable board, we have 9.6 bits left to guess after the full number of trials, which is 1.5 bits more than in the base case. To conclude, we have shown a new fault injection attack on the error correction part of a puff key storage system, and that it is feasible and can be more powerful than the side channel attack. We have also looked into masking, which might be there as a side channel countermeasure, and have concluded that it's very difficult to get right, and it's the delay matching is too close to be practical for real implementation. Then we have looked at helper data manipulation in our last attack scenario and have seen, okay, the specific decoder behavior where you got data dependency because over a wide range of helper data bit flips also makes it possible to carry out the attack, even if you cannot manipulate the helper data. So that doesn't always help either. So far, so good. The paper contains some more information on the attack preparation. So what the profiling looks like and how you can extract and compensate a static path offset, but also more information about helper data manipulation schemes which might be used to cleverly compensate inaccuracies during the glitching. And then the last step of the attack, how do you error correct something you extracted using the ECC itself. We also took a short look at other secure sketches like the fuzzy extractor or syndrome construction here. All right, with that, I would conclude my talk, and I'm keen to answer your questions.
Thank you, Jonas. So we have time for some questions now.
I believe you said you simulated a puff instead of implementing one. Was it really hard to implement one? Did you try to get some open source puff, or what was? I understand there's benefits to simulation. I'm just wondering if you tried to actually implement some kind of puff on the FPGA.
It wouldn't have been that hard. So we already have puff implementation we could have used. Basically, it's just that the puff typically is slow operation, and by the time the decoding starts, you would expect it to be finished. Or if it's running in parallel, then you might change a single bit in the puff, and it wouldn't matter that much. So it's basically it doesn't matter in the end if the puff is there or not. And if you use a register, we also have the benefit of being very flexible in choosing or in experimenting with random keys.
Any other questions? I have one question. So in the assumption part, like you mentioned that you push the ECC to its limit. So how can you ensure that when you have a black box device?
So basically, as a first step, what you can do is, so you don't know how many errors there already are. So that's a fundamental problem here. And you need to know, am I at the limit or not? So what you do first is you manipulate the helper data only without introducing any glitch. And then you see, okay, one more bit flip and it's failing. So that was the limit. That's roughly speaking what you can do here.
All right. Thank you, Jonas. Let's thank the speaker again. So the second talk is titled The Wiretap Channel for Capacitive Probe-Based Security Enclosure. The authors are Katrin Garb, Marvin Himrishi, Ludwig Kusner, and Christoph Frisch. And the talk will be given by Katrin Garb.
Is it working? Yeah, okay, cool. All right. So this is also working, very good. So hello everyone, my name is Katrin Garb. I'm currently a PhD student at the Technical University of Munich. And the topic that I'm going to speak about today is how to construct a wiretap channel for capacitive puff-based enclosures. And the goal of this work was basically to construct a tamper-sensitive error correction code for this specific puff that is able to distinguish between attack effects and the regular behavior. And this is joint work together with Marvin Himrishi, Ludwig Kürzinger, and Christoph Frisch. So the outline of my talk is as follows. First, I'll give a short overview on capacitive puff-based enclosures. Then I'll speak a bit about a system model. So this means how can the puff response be modeled considering environmental influences and attack effects. And from this system model, we constructed a wiretap channel. And I'm going to explain how we did that. And then in the end, I'll summarize the results that we obtained. So let's first take a look at capacitive puff-based enclosures and their motivation. So in high security applications, you will come across cryptographic modules and hardware security modules. And according to different standards, these modules require a physical boundary in order to protect these modules from physical manipulation. And these boundaries can come in the form of covers or enclosures or coatings. And so here in the picture, you see an example of a battery-backed HSM. So these HSMs have been around for a while. And here you have, this is the cover that protects a certain part of the PCB. And within this cover, you have a mesh of traces, a mesh of electrodes whose resistivity you continuously measure and monitor in order to determine whether a temper event has occurred. And the problem with this is that you need a continuous power supply in the form of a battery. And this comes with a reduced lifetime and a higher sensitivity towards external influences. And so to overcome these issues, enclosures based on physical unclonable functions were developed. And a puff or a physical unclonable function can be seen as the fingerprint of an object that stems from minuscule manufacturing variations. And these manufacturing variations can, for instance, be the capacitance. And since you're relying on these physical properties, on these minuscule manufacturing variations, you no longer need to continuously monitor your enclosure, and so you get rid of the battery. Here you can see an overview of the electrode mesh of the capacitive enclosure. So you basically have 32 electrodes that are arranged in a meander structure, and they overlap and form small capacitors. And in total, you will have 16 times 16, so 256 absolute capacitances. But these absolute capacitances depend on global manufacturing variations. So you might be able to even derive which batch this enclosure belongs to. So to remove this dependency, you subtract these capacitances and you end up with 128 differential capacitances that form the puff response. And this puff response will be different for each enclosure. And from the puff response, you generate a key. And so now if you are trying to attack the enclosure, for instance, with a 300 micrometer drill, what will happen is that you destroy 2 of these electrodes since their width and distance is 100 micrometers. So what happens is that the puff response will change and the key will also change. And this is also the attack scenario that we're going to focus on in the following analysis. And we are well aware that there are many other types of physical attacks for the enclosure, and we also published a paper on that. But the thing is that, so for instance, if you go to smaller drilling diameters, you will always need additional physical countermeasures, and it's not really the job of the software alone to take care of that. So, all right, so after this short overview, let's now come to the statement of the problem that we are trying to tackle here. So in order to reliably reproduce the puff response, you need error correction codes. So if you, under normal circumstances, if there's no temp event, you want your puff response to be the same, your key to be the same, no matter what the temperature in the room is, no matter what the humidity in the room is, and to compensate that, to ensure that you incorporate error correction codes. And now, if you're correcting the environmental effects, the problem is how do you ensure that you're not correcting an attack? And this is actually a non-trivial problem that we try to tackle through a wiretap channel implementation. And there have been previous wiretap channel implementations in the context of puffs, but they focused on binary silicon puffs, and we have an analog puff. And they also had a completely different use case because they focused on debiasing unstable or biased puff bits. And our goal here is to construct a tamper-sensitive error correction code. And we did that by first taking a look at the system model. So how can the puff response be modeled considering thermal influences and attack effects, considering all post-processing steps of the puff. And then we took the system model to construct a wiretap channel with QRE polder codes. And the goal here was to optimize the error correction for the puff and to construct a code through a Monte Carlo simulation. And then in the end, to get also a measure of how good the code construction is. So what is the security level of the code construction? How much entropy is left for the puff secret? All right, so let's now first take a look at the system model. And you cannot take a system model without, cannot take a look at that without considering the post-processing. So here you have the following steps. You start with measuring the puff response. And then you perform the first post-processing step, which we will refer to as normalization. So what you do here is you have certain electrode groups that will have an offset. And that is because these electrodes have different widths. So there are different currents that go over these electrodes. And so you will have certain offsets that, so to say, leak a bit of information about your puff. And you want to remove these offsets. So, and this you do through the normalization. And then the step after that is to quantize the puff. In our case, we're using a Curie alphabet. So we're working on the symbol level. And then this quantized puff is the input to the key generation. In our case, we're using the fuzzy commitment scheme. So let's now take a look at the different post-processing steps. Here we see the raw data for a single enclosure. So this might be different for another enclosure. And yeah, so these are temperature measurements for minus 20 degrees to plus 60 degrees. And so this is the same temperature range for both pictures. And on the left, you can see the absolute capacitance in the picofarad range. However, as I told you before, this depends on global manufacturing variations. So what we're actually going to work with is the picture on the right, which is the differential capacitance in the femtofarad range, which is mapped to minus 10,000 to plus 10,000 points. So, and now if you perform, so this is the raw data. And now if you perform the first post-processing step, the normalization, what will happen? So here on top, you see the raw data. So these are different distributions for different temperatures and also the Gaussian fit. And on the bottom, you see the normalized data. So what the normalization does, it changes the mean of the distribution and it also narrows the distribution. However, it doesn't narrow it down completely, because between the distribution at 20 degrees and the distribution at 60 degrees, you will still have a difference in the standard deviation of 207 points. And you can do the same analysis for the attack data. So here you see the change in differential capacitance for a 300 micrometer drilling attack. And you see that there are two electrode groups that are affected by this. And the attack has two effects. So first, it creates these offsets. It shifts these data away from the center. And it also creates burst errors. So you see these points are no longer a straight line, but they're kind of all over the place. And the normalization, so the raw data is the orange one, and the normalized one is normalized data is the blue, is depicted in blue. So the normalization will reduce these offsets, but it will not affect the burst errors as such. And what the attack also does, it broadens the distribution. So here you see the raw data on top. So this is the data comparing before the attack to after the attack. And you also have the Gaussian fits here. And you see that, below is data, the normalized data, and you see that the distribution is, the broadening of the distribution is reduced through the normalization. However, you still have a difference in the standard deviation of 787 points, which is still larger than for thermal changes. So the takeaway message from this part is basically that we are able to visibly distinguish between the regular behavior influenced by thermal changes and an attack. And as soon as you can make this distinction, you can model your system through a wiretap channel. So the wiretap channel was introduced by Weiner in 1975. And what Weiner assumed is that there are two channels. There's one main channel where the information is transmitted, and there's the second channel where the attacker intercepts the transmission on the main channel. And this is our adaptation of the wiretap channel for the capacitive enclosure. So we have the information transmitted on the main channel, which in our case is influenced by thermal effects and noise. So on this channel, we have a certain error probability P1. And on the second channel, we will additionally have the effects through an attack. So this is why we have a different error probability P2 here. And the goal now is to hide this information on the main channel from the attacker through the noise on the second channel. And the way to construct such a white channel is, we use QR polar codes with successive cancellation and successive cancellation list decoding. And we derived a probability matrix from the system model. So this is the probability matrix for all symbol transitions. So this is basically the channel law. And we did that for different numbers of intervals. And then we constructed the code through a Monte Carlo simulation. So what we did here is you take the puff response XORed with the helper data W. So this is the helper data from the key generation. And then after the polar transformation, what happens is that your physical channel described by the matrix P will be split into many virtual channels. This is what the polar transform does. And so now you can take a look at these virtual channels and check, okay, which of them are bad for the attacker and for the legitimate channel. And over these, you transmit known values. So in our case, zeros. And from the remaining channels, you check, okay, which ones are good for the attacker. And over those, you transmit random symbols. And over the remaining virtual channels, you transmit information symbols. And these channels here are bad for the attacker and rather good for the legitimate channel. And so what the attacker is left with is basically, so since these values are known anyway, and we don't consider them, either noisy data or either random data or noisy data. And for this code construction, we calculated two entropies, the attacker entropy and the secret entropy. And here is an excerpt of the results that we obtained. So for both decoders and 8 and 32 intervals, and the third column is the frame error rate. So this is the probability of a wrongly decoded puff secret. We obtained these entropies. So the attacker entropy of 100 bits. What does this mean? Well, this entropy is directly related to the security level of the code. So to the 100 denotes the brute force effort for an attacker in terms of the decoding complexity, because we have to assume that the attacker knows the error correction, or well, at least he knows now. And for this security level, we still achieve, for instance, for 8 intervals, we achieve 306, we preserve 306 bits of entropy for the puff secret. And this was also one of the main results. So to summarize what we did, we provided a system model for the puff response considering thermal changes and the effect of an attack. Then from the system model, we constructed a Y-tip channel for the enclosure using QR polar codes. And we did this through a Monte Carlo simulation. And for the Monte Carlo simulation, we obtained a security level of 100 bits while preserving 306 bits of entropy for the puff secret. And so in general, I think that the Y-type channel construction could also be interesting for other tamper-sensitive puffs, as long as you're able to distinguish between the regular case and the attack effects. So thank you for your attention, and that was my talk.
So we have time for some questions now.
So suppose I use your technology for an industrial control device, right? And some of them in the field fail, right? So I get the, say, microprocessor with your capacitive enclosure. How do I debug it, right? I need to open it up to debug it. So, or am I prevented from debugging or failure analysis because the puff will deny access?
You know, there are two things. First of all, normally you don't open it up. You also didn't open up the battery-backed ones. But so your concern is if you envelop the whole things, basically, how do you get access to it, right? And for this purpose, so unfortunately, I removed the picture from my backup slides. But the thing is that we have an FCC cable that is wrapped around the device together with the enclosure, because you need to, for instance, if you use your HSM, to secure communication, you need to be able to communicate. So you need an external connection. And so you have to take care, you have to really separate the encryption part and all the security part in the software. So, but there's an external connection that you could access it, the device. Yeah, I don't know if that answers your question.
I mean, the basic question is if you can debug the system, right? Could the attacker use that technique, the debugging technique that you provide, to now attack, right? So it's a problem with practical in-field devices when you use puffs to deny access. It's
well, you don't have access to the security part of the underlying software, but I mean, you envelop another host system into this this whole enclosure. So there's a certain part of the software that allows for applications that access all basically the puff information. So I mean, I'm not really sure. What do you want to debug exactly?
the devices that fail. I want to debug the devices that fail.
Okay,
I'm a company,
okay,
right?
that
I
is no
produce
problem because
1,000 and
okay,
10
no, I
of
get
them
it.
fail.
Okay,
And it's
because
controlling the power grid. You know, how do I fix it?
so you can well, you cannot physically access it. That's the whole point of an HSM. But the host system itself you can access. This is, but the puff part is, so to say, separated and not accessible in that sense. Yeah. Okay. Here we go.
Hi, thanks for the great talk. I have two questions.
Yeah.
First, what would be the probability that an attacker can still bypass your wiretap chat, you know, your coding? And in order to decrease that probability, should we increase the code length or increase the measurement resolution? What would be the solution?
That's a very good question and also a tricky one, because there are many factors that determine the code design. So you've seen in the beginning that the post-processing, I mean, if you do a different post-processing, you have different you're working with different data, and then you have to model it differently. But there's another thing that I didn't tell you, that is that also the quantization, the way that you choose your quantization is also relevant, because so here, because the first thing we tried is we said, okay, let's try binary, let's try with binary Polar code, and then we tried gray encoding, and we figured out, oh my God, this doesn't work, because we couldn't really distinguish at a certain number of intervals between an attack and a temperature effect. And that's because, I mean, we also tried this with other binary encoding. So you can basically, so after, if the error gets too large, you will have this effect, because you no longer have like 1 bit of change. So you have to consider how do you quantize it? How do you optimize your quantization? Can you optimize the post-processing steps? Could you maybe do the normalization in hardware? And then, of course, yeah, the coding complexity depends also on what is your list size. But then you have, I mean, you also have this trade-off. Okay, how long is my list? But how long does it take to actually decode this? So there's so many factors that are going into this. Is kind of, yeah. I don't know whether this answered the question, but
Thank you.
okay.
Yeah, so I have a question on the physical realization. In the papers, the pictures you always shown were like always like fairly small, like couple centimeters by a couple centimeters devices. Like, what is limiting the scaling of this security envelope to larger sizes? Is it the manufacturing of the foil, or is it a degradation in like the signal noise ratio for like attack detection, that with like larger foils you don't see that anymore?
Yeah, you're right. We always have like, I don't know how much it is, like 4 to 5 centimeter HSMs that we're working with, because the enclosure size at currently is 18.5 centimeters times 9 centimeters. And the only reason for that is because this enclosure is fabricated at the Fraunhofer EMFT, and they at the time that they were fabricated only had a mask that was it was restricted by the production process itself, but technically you could produce larger enclosures, so I don't see any problem doing that. Yeah.
All right. I think we are right on time now. So thank you, Catherine.
Okay.
So the next talk is titled No Time to Die, Integrity Check for Zero Trust Triplet-Based System using Between Die Delay Puffs. The authors are Alexa Derrick and Daniel Holcomb, and the talk will be given by Alexa.
All right, so hey everybody. This talk is about integrity checking of chiplet-based systems using between die delay puffs. My name is Alexa. I worked on this paper with my professor Daniel, and we want to give a huge thanks to MITRE for actually funding us. So to kind of just give you like a brief introduction, the industry is moving towards using chiplets instead of monolithic dies. And one of the reasons is because it's cheaper. But essentially the modularity of chiplets for us in this room, what this means is that it brings in a set of new challenges and security threats. So in this work, I look at the idea, I and my professor, we look at the idea of using between die delay puffs as a security primitive for chiplets. So what is a chiplet? Chiplet is basically just a separately produced silicon die. And so what you would do is that you would take multiple dies and you would put them together on a silicon interposer to actually create a larger system. And the benefits of this are many. One of the main benefits is if you're trying to build multiple systems, you can essentially mix and match chiplets. And likewise, because each chiplet is produced separately, you can use cost-appropriate nodes for each one of them. But what basically all of it boils down to is that now your yield goes up, and then which essentially means that you're making more money. And kind of to just drive the point home and to essentially show you that I'm not like lying to you, there's a bunch of examples out there right now. These include some AMD CPUs, and there's an upcoming line of Intel CPUs and a bunch of FPGAs as well. So when you essentially take a die and you split it into multiple chiplets, you create a problem. It's not a problem, but essentially you open up many new attack vectors. And so some examples that I'm going to give you, depending on where your chiplet, because each chiplet, like I said, is produced separately, depending on where they're actually coming from, you could have Trojans in it. Likewise, now because you're going to have between these chiplets, you're going to have wires. These wires are much easier to actually probe, so probing becomes an issue. And then there's this new threat that we call die swapping. Essentially, somebody can take your system, break it apart, and then mix and match different dies. And finally, most of you are going to be excited about, there's going to be new side channels, for example, side channels across different dies. So what all of this, again, boils down to is that chiplets cannot essentially assume that they're operating in a friendly environment, and there needs to be some sort of root of trust. And people have tried addressing this. For example, you can treat each chiplet as its own chip, and then you can use existing solutions like crypto and puffs. Or you can, people have also tried making what they call a secure by construction interposer. But the problem with all of these is that you increase design complexity. And that essentially means that it essentially defeats the purpose of having chiplets in the first place. So in this work, we try to use between die delays as sort of a security primitive for system level security. And we mainly try to address physical threats, which means probing, die swapping, man in the middle attacks. All the other ones, they're like left to somebody else. So I'm going to talk about measuring delay. And how do you do that? So the reason this is possible is because these dies, or chiplets, they actually use what we call source synchronous clocking. So when you have two chiplets, when you send the data from one chiplet to the other, you also, with the data, you also send the clock. And so wires, essentially, they will go from the transmitting chiplet through the interposer and then to the receive chiplet. On the receive chiplet, you're going to have registers, and you're also going to have tunable delay elements, which they let you take the transmitter clock and deskew it so that you can sample data at the right time. And then if you look at there's a bunch of different standards. And then if you look at the standards, when I say standards, I mean standards for communication. And when you look at them, all of them essentially have these elements. So this means that the approach that I'm going to be talking about is going to be pretty universal. So how do you actually measure delay? Look at the diagram in the top right. So you have two flops, and then you have two clocks. The blue clock is the clock on the transmit chiplet. The red clock is the clock that we actually transmit across. And so when you transmit something, say for example, you're transmitting a rising edge, you're gonna that edge is actually going to take some time to actually propagate, right? So once you sample it, you're sampling it with the red clock, and the red clock is essentially just a delayed version of the blue clock. And if you think back, what was it, 2 slides ago, I said that we can control the red clock because we have the tunable delay element on there, right? So if the skew between the blue clock and the red clock is really small, you're going to be failing to actually sample the correct value. You're going to be sampling 0 every time. Now, as you increase that skew, you're going to be essentially pushing the sampling time back. And you're going to be with each time, essentially, you push it back with an increasing probability, you will be sampling the correct value until eventually you're like meeting setup time every time. And every time you're sampling the correct value. And so in our work, we say that delay is the point in time at which you're sampling the correct value 50% of the time. And so what we use to actually build this system and actually test everything is FPGAs. And I assume most of you know what FPGAs are, but the reason we do that is because they let you control the clock, and they also let you basically do whatever you want. We use mainly Xilinx FPGAs, and so you can see one pictured in the top right. You can see that these FPGAs, Vertex Ultra Plus, these are actually based on chiplets. So they're basically what we want. And I should mention, I'm going to give you a couple just notes here. These chiplets, Xilinx actually calls them superlogic regions. So whenever you see SLR, just think chiplet. And then also the wires that go through the interposer, they call them super long lines, which, you know, whatever. But whenever you see SLL, think wires. So in lab, so actually to test this locally, we have basically a development board, and then to actually test it at scale, because it's a puff. So you need more FPGAs, and these FPGAs, they can be expensive. So to actually test it at scale, we use AWS, or essentially that cloud FPGAs. You can essentially rent them out. And so I'm going to talk about the actual design now. So this is the design. It is column-based, and I will explain what I mean by that. But you don't really have to remember, like you don't have to actually understand what's happening here. I'll give you a couple hints. So you have 2 chiplets, and between them you have these wires. And these wires actually go through the interposer. So this is the wires that we care about. You also have these MMCMs, which essentially they let you control the clock. So you can essentially do a phase sweep with them. And then on each die, we have a pattern generator. On the TX die, this pattern generator, we essentially just transmitted. If you think, 2 slides back, I was talking about a rising edge. So think about it. This pattern generator just generates a rising edge, for example. On the receive die, we also have the same pattern generator. And it is used to essentially, when we transmit the pattern across, we use the receive pattern generator to actually check it. So you also need some extra logic to actually compare the two. And so this is what the actual design looks like when you put it on an FPGA. Once again, I want to stress a couple things. First, the white rectangles that you see, those are basically instances of my design that I described here. And we have 6 of them. So in total, we have almost 300 wires, right? And then once again, I want to make sure that you guys see there's two chiplets there. There's the TX chiplet, which is like the top chiplet, and then there's the RX chiplet, which is like the bottom chiplet, right? And then my design sits like right on the edge. So that's where those wires actually go through the interposer, they cross to the other die. And then you can actually get those delays of each of those, wires. And then when you put them in a nice graph, that's what you get. And I should also mention, I guess we're using less than 2% of the actual, of the total number of wires, which is like super lightweight, right? And so these delays, they can vary. They can be between 630 and 720 picoseconds. Once again, referencing the figure in the bottom left, if you take a single wire and you measure it like again and again, the difference between those two measurements is going to be around 0.5 picoseconds. And then if you take that same wire and you look at different FPGAs, that difference is like 30 picoseconds. So that's like 60 times larger, which is nice. And then we also tried like getting rid of some of the biases. And once you do that, you'll still get around 6 picoseconds, which is what, 10-ish or something, I don't know, it's math. But essentially you have these delays and then 0.5 picoseconds is like really good, right? But we can do better. And the way you do better is by essentially, instead of considering just a single wire, you will consider pairs of wires. So the reason you do that is, if you think about it, when you're measuring the delay of a single wire, you're racing the wire delay against the clock, right? And those things there, essentially, if you have environmental factors that you can't account for, they're like impacted differently. So in the bottom left, there's a plot shows you that essentially, if you just consider a single wire, your delay is going to just like drift around. Now, if you take two wires and you take their difference, you subtract out the clock, and so your delay becomes much more stable. And so the thing that we actually use through, like for the rest of the presentation, whenever I say delay, I mean differences. I mean the difference of like pairs of, hold on. Whenever I say delay, I mean essentially differential delay. You take two wires, you take their difference. And so this is what the design actually looks like when you measure it. So we had 20 FPGAs. We tried using more. They told us like, no, we don't have that many available. This is the same FPGA that we use for local testing. So between like doing it in the cloud and doing it locally, nothing actually changes. So the top plot shows you what we get when we essentially do a bunch of comparisons for just a single wire. And then it's not really that impressive, but when you do it for like all the wires across the entire chip, you get this really nice gap between the two distributions. So the blue distribution is the within class distribution, and then the red distribution is the between class distribution, or same FPGAs and different FPGAs. And the gap, the fact that we have this nice gap means that we have a unique and reliable fingerprint. And so in our case, it was because it was only 20 FPGAs, I guess it was perfect. So we wanted to essentially see how perfect it actually was. And what we realized is that these distributions, so the bottom one, they're actually fairly normal. So we fit a normal curve to each of those. And what we found, we essentially looked for the point where the false positive and false negative probabilities are equal, which happens at around 150 picoseconds. And so when you look at that, you find that your type 1 and type 2 error rates are basically astronomically small, which once again confirms that we have a unique and reliable fingerprint. And so I'm going to talk about some characterization experiments that we actually did. So the first one was, you guys remember that I talked about differential delay, right? So the first thing that we looked at is essentially changing the clock tree and seeing how that actually impacts what we get out. So I have two designs here in the bottom. At the bottom, you can see that both of them are essentially basically the same except for the clock tree. And once you change it, we essentially change the clock tree, we get delays out, you map it, and you get this nice positive correlation, which is like pretty strong, right? So this tells us that this essentially tells us that the puff that we have is not that sensitive to the clock. So now we also tried transmitting, like I talked about, we transmit rising edges, right? So we also tried transmitting like falling edges. And the reason is that when you transmit rising edges and transmit falling edges, you're using different transistors to actually drive the wire, and you're using different transistors to actually sample the wire. but the wire actually stays the same. And so this kind of tells us where this entropy is actually coming from. So once we did that, we found you get this nice plot that actually tells you that there's like no correlation, which means that transistors, in our case, are a significant source of entropy. And so we tried also doing the same thing, but driving the wire in the opposite direction. So normally you're driving it, for example, if you look at the bottom, you're driving it left to right. So we tried driving it like right to left, and you kind of get the same thing, because once again, you're using different transistors and to drive the wire, and then you're using different transistors to actually sample the wire. But now you also have the fact that these dies are essentially different. So the correlation that we get, once again, is like really weak, but it's weaker than what we had before. And this is because essentially we're using different dies, right? So finally, we looked at heat, because as you know, that heat can change delays. So the way we did this is by placing down a bunch of ring oscillators. And we had a lot of them, but you could like turn them on in groups. So once we tried doing that, you can see that the temperature of the die actually goes up, right? And so delays also go up. But what you can notice, and what's interesting, is that not all of them go up like by the same amount. Some of them like go up much. Some of them increase much more than others. And so this for us is bad because we're using differential delays, right? So they're going to drift all over the place. So what you can do is, for each of those, fortunately, you can essentially calculate a compensation factor, and then you can apply it. And then once you do that, you essentially they're stable again. I should mention that we're not using any sort of like temperature sensor. This is done with like averages and stuff. So there has to be some sort of enrollment procedure if you're to use this, but you don't need any extra hardware, right? So that's cool. Finally, we wanted to test the impact of aging, because aging, like heat, can change delay, right? So what we did for that is we took all of our wires, which, if you remember, we have like 300 of them. We split them into two groups. One group, when we're not transmitting anything, we're pulling it high. The other group, when we're not transmitting anything, we're pulling it low. And so we put the FPGA in the heat chamber. This speeds up the aging process. And so we ran it for like 3 hours according to the plot. And what we tried essentially to see is that if those two groups, if the averages of those two groups will diverge, what we found is that that doesn't happen. So in our case, we can say that aging does not really have any effect on our design. And so kind of to just like dial it back, we showed you a design that is capable of essentially measuring delay down to a picosecond, right? So that's bad news if you're trying to do anything malicious, because if you're trying to do anything like with physical probing, you're going to have to do so in a way such that you're not changing the delay of any particular wire by more than a couple picos. And then if you're trying to swap the dies, that's also not going to work, bro, because if you do that, essentially, because the source of our entropy is, because transistors are one of the sources of our entropy, if you try doing that, you're going to mess up the delay again. So in conclusion, we presented a security primitive to extract delay fingerprints from connections between chiplets. We tried building this design on the FPGA, and then we did it in the cloud as well to essentially scale it up. And then we performed analysis across a variety of factors to identify essentially the sources of entropy in the system. Thanks. I'll take questions now.
We have time for one short question, I think.
Wait, what?
So my basic question is twofold. Your source of entropy are wire measurements with transistors doing the measuring. And then the question is, did you consider machine learning where, because you have, I forget the exact number, say 1,000 wires, you do differences to figure out the behavior of the 1,000 wires, and then you could machine learn the puff. Have you considered that as an attack vector?
I heard it's possible, but to be honest, I'm not an expert on machine learning, so I can't really comment on it. Sorry.
All right. So we can move to the next talk now. Thanks, Alexa. And the last talk for this session today. Yes, thank you. So the last talk is a recorded video, but the speaker Takashi is actually online to take the questions. So the title of the talk is Redshift: Manipulating Signal Propagation Delay via Continuous Wave Lasers. The authors are Kohei Yamashita, Benjamin Sear, Kevin Fu, Wayne Burleson, and Takashi Sugawara. And Takashi will be the speaker.
Hi, I am Takeshi Sugawara, and I'm going to talk about Redshift, manipulating signal propagation delay via continuous wave lasers. This is a joint research work with Kohei Yamashita, my student, Benjamin Sear and Kevin Hu from University of Michigan, Ann Arbor, and Wayne Bolson from University of Massachusetts, Amherst. As you may already know, laser photoinjection is an attack that induces bit flips in digital circuits using a laser. It has a great spatial resolution, and we can even flip individual bits in memory. In the meantime, the impact is limited to a small region, meaning that detection-based countermeasure is challenging compared to other methods like clock glitching that affect globally. Successful bit flip needs a high peak power because a bit flip occurs only when a photocurrent exceeds a certain threshold that overwhelms a legitimate transistor current. Commercial laser stations solve this problem by using short pulse and high power lasers. It is very sophisticated and the state-of-the-art in optical engineering. Meanwhile, this comes with expensive attack cost, and commercial laser stations cost typically more than $100,000. This is a major drawback of laser photoinjection. Some years ago, we proposed light commands, which is an extension of laser photoinjection, to microphones. MEMS microphones receive fake audio when illuminated with amplitude-modulated laser, which results in silent voice command injection attack on smart speakers. An Asic inside a microphone package was one of the causes. We surprised with its extreme sensitivity. A weak continuous wave laser, similar to a laser pointer, was sufficient for the attack. There's an important gap between the two cases. On the one hand, conventional laser photoinjection needs an optimized high-power and short-pulse laser. On the other hand, a weak continuous wave laser was sufficient for the audio injection attack. We conjecture that analog circuits can be more sensitive to light because they handle tiny voltage and current signals. Motivated by this, we started this research project by focusing on delay-sensitive circuits, commonly used for realizing analog domain functions using digital components only. We propose a new attack called Redshift that manipulates signal propagation delay via continuous wave lasers. This is the outline. We first discuss oscillator frequency shift. We show our cheap laser setup and frequency manipulation experiment. Then we discuss its advantage compared with conventional laser photoinjection attacks. Then we discuss its application to puffs in the latter half. The attack is based on previous attack on SRAM path, so we begin with briefly recalling the path-based key storage and its previous attack. Then we show preliminary state biasing experiments with ring oscillator and arbiter paths. Then we show the state recovery experiments. We finally discuss the causality and countermeasures, followed by the conclusion. We begin by showing our chip laser setup. The idea is to upgrade a common microscope with a laser diode. We designed a laser module with collimation optics and an adapter compatible with a standard C-mount camera port as shown in the left figure. The figure on the right is our microscope with the laser module installed. Controlling a laser diode is very simple, and we can control the laser power through driving DC current in the same way as LED dimming. We use a laser current driver and a function generator to programmatically control the laser power. The first experiment is frequency shifts in ring oscillators in custom Asic chips. Our Asic has a simple ring oscillator. We put a depackaged Asic chip under the microscope and aim the laser on the oscillator. Then we gradually increase the laser power while measuring the oscillation frequency. These two figures show the relationship between the frequency and injected laser power. They clearly show that the frequency decreases almost linearly with the injected laser power. The starting frequency was around 30 MHz, and we could decrease it down to 5 MHz with 1.75 milliwatt laser power, which is weaker than that of a laser pointer. The next experiment is frequency shifts in clock oscillators on commercial microcontrollers. We repeated the previous experiments with microcontrollers configured to emit clock signals at their GPIO pins. Then we observed similar frequency shifts in older targets from different vendors. There's a variety in the sensitivity and linearity. The one has high linearity and less sensitivity, and the others have lowest linearity and high sensitivity. So what is the advantage of Redshift compared to conventional laser photon injection attacks? The first one is to extend the target of laser attacks from digital circuits to delay-sensitive analog circuits. Second, it can be more stealthy in a sense, evading laser detectors configured for conventional pulse lasers. The required laser power can be less than 1/1000, so it can be lower than a detection threshold configured for the previous ones. Finally, setup can be much cheaper. We can cheaply upgrade a common microscope with a DIY laser module. Our setup is around $5,000, mostly for the microscope, which is in contrast to the conventional laser stations, typically cost more than $100,000. This makes the difference in attack classification in the common criteria certification. How can an attacker exploit Redshift? In this particular project, we focus on attacking paths and we'll see it in the latter part. Before that, we quickly review other possible extensions. Redshift can disrupt oscillator-based random number generators in the same way as frequency injection attack. Also, Redshift on system clock can cause synchronization problem, which ends up with digital errors. Finally, Redshift can induce false positives and negatives in on-chip sensors, such as EM probe detectors or glitch detectors, because they commonly use oscillators as a sensing principle. We briefly recall path and path-based key storage. We call path state a device-unique ID generated by a path from manufacturing variation, and we call path key a cryptographic key generated from a path state with error correction. Finally, path-based key storage is an encapsulation of a pre-shared key with a path key. The path-based key storage is one of the most important path applications. The keys appear only after the chip is turned on, providing the protection against reverse engineering attacks. Our attack is based on Zaitoni et al.'s SRAM path attack exploiting remanence effect. The idea is to bias SRAM path states by gradually increasing the width of reset pulses, which enables state recovery attack in path-based key storage. SRAM path uses the power on initial state as a path state. Suppose the SRAM region previously contains all zeros before reset. If the reset pulse is long enough, it works correctly and the SRAM comes back to the device-specific initial state. If a reset pulse is short enough, SRAM holds the previous values by the remanence effect, resulting in all zero path state. A pulse width in between results in a path state in between. As a result, the attacker can bias Hamming weights in the path states by gradually increasing the reset pulse width. With a sequence of intermediate states, an attacker can find one from the previous one with exhaustive neighbor search. Repeating this process recursively starting from all zeros, the attacker will eventually reach the legitimate secret state. The attack works only with indirect access to crypto services on the bottom. The attacker guesses the path state, emulate error correction and crypto to generate a hypothetical response and compare it with a recorded one. The idea is to use Redshift to induce similar biases in delay paths. A simple target is a ring oscillator path with a fixed reference oscillator. For each target oscillator, the path compares its frequency with that of a reference oscillator, and the path outputs 0 if a target oscillator is faster and outputs 1 otherwise. The path generates a long response by repeating this with many target oscillators. If we slow down the reference oscillator with Redshift, then the threshold moves to the left and the path state has more zeros. We verify the attack with experiments. The target is ring oscillators in our Asic chips that use the previous ring oscillators internally. We eliminate the reference oscillator while the target paths generate 256-bit states. These graphs show the relationship between the injected laser power and the Hamming weights in the 256-bit states. We can clearly see that Hamming weight decreases as we increase laser power. The path states eventually reaches all zeros with 0.3 or 0.6 milliwatt, which is far below the power of a laser pointer. Similar Hamming weight biasing is possible with arbiter paths, because Redshift on an arbiter circuit makes one path slower than another. We verify it with arbiter paths on our Asic chips. Similar to the previous experiments, we illuminate the arbiter circuits while the target paths are generating 256-bit states. These graphs show the relationship between the injected laser power and Hamming weights. And the Hamming weights decreases as we increase the laser power in the same way as the previous experiments. We verify the state recovery attack with error correction and crypto schemes. We use a simple error correction scheme to generate a 128-bit key from the 256-bit path states by selecting stable bits and making bitwise majority voting. Then we generate challenge and response pairs using AES-128 using the path protected key. In the experiment, we illuminate the target path with a laser and query the crypto service 5 times. Then we repeat the same measurement by gradually increasing the laser power. We do not go deeper into the search algorithm, but the idea is to iteratively find next states with neighbor search, starting from 0 until we get a legitimate secret state in the same way as the previous attack. This table summarizes the result. We successfully recovered 128-bit secret key in all the cases with less than 1 second of computation. The distance explored in neighbor search is the computational bottleneck because it grows combinatorially. The table also shows Dmax, which is the maximum distance to next states. In our experiment, the next states were always found within 1 or 2-bit distances. The measurement is dense enough, and that's why the search finished so quickly. We can explain Redshift with the conventional model that models photocurrent as a current source in parallel to a transistor. With this current source, a part of the driving current is wasted to the ground, meaning that the time needed to charge the load capacitance becomes longer. Actually, failure analysis technique called laser-assisted device alteration also changes transistor speed with laser illumination. We can use a theory in this field for more precise physical modeling. We proposed countermeasures in several different levels. On-chip sensors are still promising. The one for the pulse lasers are not necessarily effective, but its extension to continuous wave laser would be possible with additional techniques such as integration over time. If we focus on ring oscillator, avoiding a fixed reference oscillator will make the attack more challenging. For example, we can use pairwise comparison. The path state recovery attack was possible because the chip continues its operation even with a wrong key. Detecting a wrong path keys and suspending crypto services can be a countermeasure. Finally, the path attacker needs details about error correction and crypto. Hiding the details with hardware obfuscation techniques can be another countermeasure. We propose a new attack that slows down delay-sensitive circuits with continuous wave laser and its application to path state recovery attack. There are several problems remained open, including extension to other applications and analog circuits, and further verification of the causality through experiments and simulation. Thank you for listening.
So we have time for some questions now.
Thank you for the talk.
So
Yes,
Takashi,
thank
if you
for the
can confirm if you can hear us now.
Did you say slides? Yes. Yeah.
Okay, thank you. Yes, thank you for the talk. So about the protections, concerning let's say the accuracy of the laser shot, I think you need a minimum of spatial accuracy. And in this case, do you think that the placement, the interleaving of placement, for instance, between two ring oscillators could be a protection, for instance? So there are two questions. What is the density of the, what is the accuracy of the laser shot? And is the placement a good protection? I mean, the interleaving placement.
Thank you. Yeah, great question. Let's say, so the laser spot size is determined by the diffraction limit in the objective lens. So that should be similar to the previous laser stations. But the thing is that we didn't use the maximum amplification in our case because in our setup, the step we can change the laser power was the bottleneck. So the higher magnification means a bigger step in increasing laser power. So the lower magnification was actually more advantageous in the experiment. So the accuracy of aiming depends on particular projects, but we can think of physical diffraction limit to estimate the power density we can inject. And second question is about specific placement can be a countermeasure. Let's say, so does it mean, let's say, detecting the second, using the second oscillator to detect, I'm sorry. So maybe the thing you mentioned is to compare two neighboring oscillators so that two of them are illuminated simultaneously. Is it, am I understanding correctly?
Yes, exactly, yes. You have two
Okay.
blocks, yes.
I see. So it depends on the size of the target oscillator. And we can compare the size of the circuit with the laser spot size limited by the size of the objective lens.
You mentioned a green laser and a depackaged Asic. Did you have to thin, or did you get enough light into the circuit without thinning?
Thank you for the question. All the experiments, as we can see in the figure, the injection is from the top side. So there's no thinning involved.
Right. Thanks, Takeshi. I think we are over time now. So with this, we would like to thank all the speakers of this of this session, actually. And
thank you very much.
Also, please stay for an announcement.
Thanks. So small announcement before you go to lunch. The first session after lunch is still 2 tracks. So one of them is here in Grote Aula, but the one that's normally in PDS will be in another room. Recall that was announced in the very first session of the conference. You will not know how to get there, so we will help you with that. So don't go in the PDS. Don't go in the PDS. But at 1:50, we will meet outside on the square, and we will lead you there. Okay. Enjoy lunch.